Hi, I'm Claire Newman and I'm going to talk about what it's like to work remotely on Mars. So I currently work on 3 Mars missions. The Mars Science Laboratory Curiosity rover, and you can see on the left here a self-portrait that was taken on Mars by the rover. This is actually done by taking a lot of images with a camera that's on a robotic arm, with the arm in a different position in each image, and then you can combine them to edit out the arms. So we don't have anyone on the surface obviously taking our portrait, but we can take our own, take a nice selfie. And there's a nice artist's impression of the rover on the right. I also work on the InSight lander. This is an InSight self-portrait taken on Mars, and then an illustration of how the lander looks with its deployed seismometer as well, and heat probe. And InSight is looking at the inside of Mars using seismometers to measure Marsquakes, as well as many other instruments. And the third mission I work on is the Mars 2020 mission. So I work on instruments on the Perseverance rover, but of course the Mars 2020 mission also includes the Ingenuity helicopter. So here's a great self-portrait taken again by the rover's robotic arm, showing the heli in the background. That was right after we dropped the heli off from underneath us, as you can see by the wheel tracks from where the heli is sitting. So I'm going to talk mostly about the Mars 2020 mission and the Perseverance rover here. And the science objectives for Perseverance fall into 2 categories. One is to understand the possibilities of ancient life having existed on Mars. And then the other category is more directed to preparing for humans going to Mars. And basically, one of the big objectives of the mission is to take samples of rock, soil, and atmosphere and then return these to Earth. Well, Perseverance itself will not be returning anything to Earth, but here's the plan for Mars sample return. First of all, a sample fetch rover will be sent to Mars, and it will collect the samples that have been deposited by the Perseverance rover on the surface and bring them back to a Mars ascent vehicle, and that vehicle will launch the samples into orbit, and from orbit an Earth return orbiter will capture the samples and will return them to Earth. So this is the plan for Mars sample return, and right now Perseverance is busily collecting samples that at some point, hopefully in the coming decade, will be returned to Earth for examination. Now there's loads of cool science, and I'll touch on it a little bit in this talk, but what I'm really wanting to talk about today is what does working on a Mars rover mission involve? And by the way, the background to these slides are all going to be an image of Jezero crater, which is where Perseverance landed, taken by the rover. Okay, so I work as part of the large Mars 2020 science team, and I co-lead the atmospheric science group, and we help to plan observations relating to Mars's atmosphere. So I'm going to talk about how we tell Perseverance what to do on a typical Martian day, a sol. And the key thing to understand is that we can't do things in real time, and there's several reasons why that is. One is that there's a time delay between Earth and Mars. It takes between 4 and 24 minutes for information to travel between the 2 planets, and that depends on where both of the planets are in their orbits. So it's very difficult. You can't really steer the rover in real time, and you can't do a kind of a back and forth very easily, even if you were relying on direct communication to the rover from Earth to the rover and back. But a bigger issue as well is that we really do most of our communication via orbiting spacecraft, and these relay rover data back to Earth. So we can really only see and collect data from the rover when those orbiting spacecraft have a view of the rover on the surface and can act as a relay. And that only happens for a total of about 8 minutes per sol. So all of this means, as I said, that we can't react in real time to what the rover sees or finds out. And so instead, the Mars 2020 team plans a to-do list for the rover every sol, or sometimes we plan multiple sols in a row. And that to-do list might include something like fire laser beam at rock, drive 70 meters to the northwest, look for dust devils, make oxygen, and so on. And we'll talk about some of those things later. So what happens is that we send our to-do list to Mars and the rover carries it out. There we are, firing a laser beam at a rock with the Supercam instrument. And so we tick off our item on the to-do list. And once the rover has done all those things, it sends the results back. And that's usually lots of images and other data. And it sends them up to the orbiter in orbit. And then that orbiter relays those data back to Earth. And as I said, lots of information, lots of images. And then when it gets back to Earth, the team looks at those results and then we work out what to do in the next sol. Now, this is probably not a typical day. This is, I think, taken from landing, and everyone was super excited and they're all dressed up, and this is in the big mission control type room. So what it actually looks like when the science team receives data is more like this. And this is just a sampling of some photos of Mars 2020 team members working from home during the pandemic and sitting and looking at things on their laptops and their home computers. And these days, a few more people are back into work, but they're basically doing the same thing, sitting in their offices looking at images or looking at data. And then in my house, of course, this is actually what rover planning days look a lot more like. This is my cat Sparky. As you can see, he's very deeply engrossed in what's happening, trying to be very helpful. This was actually when he had brain surgery in late 2020. He sometimes takes a little snooze during the afternoon. He typically begs for food, often during planning, but he always gets back to work. So anyway, and he's a great little companion, a little work companion. So, and there we are in March of 2020. I think that was shortly after I got over to England during the pandemic. He's helping me plan the work. Anyway, so we've talked about how we do planning on Perseverance and talked about how we send a to-do list. Now, what kind of things go on Perseverance's to-do list? Well, one obviously very big one is to drive. And this is a very cool computer simulation of part of Perseverance's first auto-nav drive. Now, the auto-nav, the automatic navigation, is very, very cool. And so basically what happens is the rover planners with the science team pick a location that we want to drive to based on images that were already sent back. And then as the rover drives, it takes images and it forms them into a map of the surface, including obstacles. And so you can see here, there are some blue lines that come out here and they find that obstacle and they tell the rover, no, we want you to avoid that. And that's when the rover uses AutoNav to decide how it's going to drive to that location. For example, in this case, to drive around a big rock. So another thing that we do, and this is a big category of things, is to look at the record of Mars's watery past. Mars was much wetter billions of years ago, and this is just one idea of what a warm and wet early Mars might have looked like. We don't know exactly what Mars looked like, but these are ideas that are suggested by where we think we might be able to see ancient shorelines and evidence of water in how things look on the surface and the kind of minerals and chemistry that we can see when we look at spectra and we look at imaging at the surface. Now, we do believe that Jezero crater was once flooded, and so this is on the left Jezero crater today, and then on the right an artist's impression of what it would have looked like billions of years ago. And one of the big reasons we believe that it was flooded is that it contains the remnants of an ancient river delta. So if you compare with this river delta on the right, which is the Mississippi River Delta, this is formed when a river reaches a lake or a sea and the water slows down and some of the sand and soil that it carries drops out. And so if this builds up in layers to form new land, it's called a delta. And it's often a very fertile region where there's a lot of biology going on. And you can see that this ancient delta, it's so old that there's even crater impacts that you can see on top of it. So this stuff has been there a really long time on Mars. So we carry a lot of instruments that look at signs of Mars's watery past on the surface. And we can look at images of rocks at different zooms. And so this just shows some of the cameras and some of the images that can be taken with the different cameras on Mars 2020. This is with Mars-Cam Z. This is an image taken with Supercam. And then there's also 2 images on the robotic arm, and Sherlock and Watson. And then this second image is from Pixel. Now we can also measure what the rocks are made of, not just image them, but also measure them. So this is Supercam using its lasers, and what it does is it sort of burns off some of the rock and turns it to kind of gases. And then we can look at the spectra, we can look at the light coming off those sort of gas version of the rock, and we can see what chemistry and what minerals are in that rock. And that tells us a lot about how that rock formed and how it may have been formed underwater or by water processes. We can even look for layers under the surface with the RIMFAX instrument. And RIMFAX is a ground-penetrating radar that is always active when we're driving along and is looking at layers subsurface. So these measurements collectively tell us things like when Jezero crater was underwater and for how long. We're also looking for signs of past life. And so that means that we're looking for things like molecules, rock structures, and other evidence that may have been created by past life forms on ancient Mars. And this is just an example from Earth. There are these things called stromatolites, which means layered rocks, and they are created by a certain type of bacteria. So these probably wouldn't look the same on Mars, but if we saw something like this, then we could say, well, you know, this looks like something that could only have been caused by some kind of a life form. And if we do find anything like this, then that's something that we would certainly want to take a sample of to send back to Earth, because, as I said earlier, another thing on our to-do list is to take samples for future return to Earth. And so on the left here, we show a sample tube, and you can see how small they are, really, the samples. They're only about 1 centimeter in diameter and a few centimeters long. But that's all that we need, because these will be pieced up into very tiny pieces probably, and then examined with lots of different techniques and microscopically, and with instruments that are just too big and too power hungry and too complicated to miniaturize and send to Mars. So the only way to do these measurements is to bring them back to Earth. And this is just one idea of how we might do the caching of the samples. I think now this is a little out of date, but the idea was that, you know, we would put some caches in one location. But now I think we're going to have a couple of caches, one that's going to be before we leave Jezero crater, and another one that's going to be with basically the same samples. Every time we take samples, we basically take 2 of everything. So the second sample cache that will be deposited onto the surface will have the same samples as the first cache plus extra ones, and it will basically be somewhere outside of the crater. But there's a real desire to cache, to take these samples and to put down this deposit of them as soon as possible, to make sure that we do it while everything's still working on the rover, so that it's there to be picked up in the future. So another thing that goes on our to-do list is to make oxygen, which is very cool. This is the first time this has been done on Mars by a technology. Most of Mars's atmosphere is carbon dioxide and there's very little oxygen, so obviously very unlike Earth. And Perseverance carries an instrument called MOXIE, and MOXIE takes some of Mars's carbon dioxide and turns it into oxygen. And so you can see here what MOXIE looks like and where it sits inside the rover. Now, this is to help prepare for the future when humans go to Mars. And you might be thinking, well, humans need oxygen to breathe, and that's true. But it's also, the idea is that liquid oxygen can be used as rocket fuel, and that can help the astronauts return to Earth. And then, of course, yes, it can also be used to provide air for the astronauts to breathe. And then another thing that Perseverance does pretty much every sol is to measure the weather, to measure clouds and to measure dustiness. And that's something that I work on the mission as an atmospheric scientist. So the main instrument that we use to do weather measurements is the Mars Environmental Dynamics Analyzer, or MEDA. And MEDA measures a huge amount of stuff. It measures winds, temperatures of the air and the surface, pressure, and humidity. And so there's actually a weather website that you can go to at the link posted here, and you can look up what the latest weather is in the crater. This just gives an example of some measurements taken by MEDA. So this shows the observed air temperatures over 6 sols, 6 Martian days in early summer. And this is in Kelvin, so it might look a little bit strange. But basically, the peak temperatures at this time of year are well below 273 Kelvin. And that's the freezing point of water. So that's pretty cold, and that's the peak temperatures. And the daily variation in temperature is about 55 Kelvin. That's about 100 degrees Fahrenheit. So if you can imagine the temperature varying by that much between daytime and nighttime, that's pretty huge. And that's the kind of thing that we only ever approach in the Earth's deserts. And that's what it's like everywhere on Mars, basically. Now, another thing we can measure with MEDA, this time with the radiation and the dust sensor that's shown here, is the type and amount of clouds and dust in the atmosphere. So the left figure here shows the fields of view, so what they're looking towards, of the photodiodes, and on the right hand side we can see the field of view of the camera, the Supercam camera that's part of this sensor as well. And basically there are 2 types of photodiodes. The ones where the field of view is shown in blue are looking basically upwards, and then the ones that's shown in where the field of view is shown in green are looking more out to the side. And so in both cases they're able to see things like blocked sunlight due to clouds or dust, or scattered sunlight due to clouds and dust. And the cool thing about the ones that look out to the side is that they are able to tell us when there are things like big dust lifting events going on, or dust devils, these dusty convective vortices sweeping past the rover. And they can even tell us what side of the rover they pass on and how they move around the rover and how they move away from us and towards us. So those photodiodes, which measure at a frequency of once per second, are really able to give us a huge amount of information about not only what's going on in the up in the atmosphere, but also what's going on in terms of surface dust lifting as well. And then the Supercam camera is able to take images of the sun, and in order to give us the dust column depth in the atmosphere, and then also to take images of clouds with its fisheye lens. We can also learn about weather from the first microphones operating on another planet. There are actually 2 on the rover. This one here is the Supercam microphone, and there's also an EDL microphone from the Entry, Descent and Landing system. And basically microphones can tell us a lot about turbulence, They can tell us about wind strength and kind of gustiness, wind variability. And what makes this sensor very interesting is that it's measuring at very high frequency, and so it can tell us about processes occurring at very high frequency, such as turbulence. It can also detect vortex passage or dust devils and measure sand grains impacting either the microphone or the nearby rover. And again, you can go online and you can find recordings of the Perseverance microphone. We also learn a huge amount about weather from all of the many rover cameras. There are over 20 cameras in total on the rover, and we use several of them to do atmospheric science. So Marscam Z took this gorgeous image of a very thin dust devil, and the navigation cameras, the nav cams, also take lots of dust devil and cloud images and dust lifting images for us. So this is some cool atmospheric imaging results from the crater. And on the top here, you can see dancing dust devils. There are about a dozen dust devils in this one movie. And you can see there's two of them near the front that move towards each other and then cross each other and then sort of fade away after that. And then the movie repeats. And at the bottom here, we can see another soul. And now we can see a whole load of other dust devils in this other location. So we are actually seeing far more dust devils at this location than we have in Gale Crater, where Curiosity is, or at InSight's landing site. Now, just as an aside, this is one of my favorite results from the Curiosity rover mission. And so in the background here, we can see Mount Sharp, which is in the middle of Gale Crater, where Curiosity landed. And these are just these hills, sort of at the foothills of the mountain. And there's this lovely dust devil that is just meandering its way along the foothills here in this short movie. And I should have said this, and the previous images are slightly enhanced by to emphasize the difference between frames. But you can actually see this one pretty clearly as well, just in the raw images. And the reason I love this one so much, I think, is not only is it a very pretty movie, but I also actually helped take this observation because I was leading atmospheric observations for this particular sol, and myself and Doug Ellison helped to pick the time and the pointing, the camera view for this lovely movie. And while we're here in Gale Crater, here are some beautiful clouds that we imaged. And again, this is a short movie, only 3 frames, of clouds that were high over Gale Crater. Now, these were actually taken after sunset. And so these are still illuminated because even though it's dark on the surface, the sun's rays are still able to reach the upper, the higher part of the atmosphere. And so these are called Noctilucent Clouds because they're taken after sunset. And I should note that Mars is cold and has very little water, but thin water ice clouds such as these are quite common. But we don't get these big fluffy convective clouds that we do on Earth, but we do get these very thin ice clouds. Now let's go back to Jezero Crater and Perseverance. Now, what we've also seen that's really exciting in Jezero Crater is these huge dust lifting events. Now, this short movie shows just 3 images that were taken by nav cams over only 30 seconds. And what this basically works out to is dust that's being raised over an area that's roughly equivalent to about 4 square kilometers. So this is a really huge dust lifting event. And we can also see dust being lifted by the Ingenuity helicopter when it takes off. Now, this is a very enhanced image, so there's a lot of sort of noise in it, but you can see that there was dust lifting when it took off, and now as it blows across the surface, you can see more dust lifting going on near the surface as the rotors stir up the dust. And just as it disappears off to the right, you can see even more dust lifting. And so let's take another look. There's some initial dust lifting. and then the dust lifting stops as it hovers, and then as it moves sideways across the surface, you can see dust being lifted again. So now that I've talked about some of the things that Perseverance can do, I thought I'd talk about what happens if things go wrong on another planet. The first one I like to call the backup brain. So missions do try to carry spares of things that can be replaced if something fails. For example, the Curiosity rover carries extra drill bits, but it doesn't carry extra wheels, partly because it would be very difficult to replace them, and partly, of course, because they're also very, very big, and it would really increase the weight and the size of the mission if you try to do that. But one thing all missions do carry is a spare onboard computer, and that's because that computer is, of course, vital for everything from driving to taking data to communicating with Earth. And this has come in particularly useful for the Curiosity rover. Now, Curiosity has a pair of identical brains, or central processing units, CPUs. And after landing in 2012, we began by using the Side A computer, but part of that side was damaged after only a few months on the surface. So we actually switched to using Side B, and we repaired Side A, and that involved removing some of its memory. So we switched from A to B. So having repaired its memory, we still kept on using Side B, but then eventually a few years later, Side B had problems. So then we switched back to Side A temporarily while we repaired it. And the reason we wanted to stay with Side B was because Side A had had some of its memory removed. So while we had to keep using Side A, we couldn't do quite as much. So as soon as Side B was repaired, we switched back to it again, and touch wood, it is still working. The second example is called wind sensor Woes, and so this is now Curiosity rover. Curiosity is sitting here in Gale Crater, and one of the things that we did with Curiosity was we drove through this gorgeous dune field. And it's the first dune field to be explored on a body other than Earth. Now, the interesting thing is that these dunes are actually moving, and you can see this in two images taken from orbit 6 years apart. You can see in the image from 2008 here that the dunes are slightly further to the north than they are in the second image from 2014. So you can see the front of the dune moving slightly to the south, and you can also see the ripples on the top of the dune moving. And to understand how these dunes formed and how they move, we really wanted to measure the winds next to them. The problem was that when we landed, one of Curiosity's wind sensors, the one pointing to the side and rear, was damaged. And that means that we only had the front-facing wind sensor available to measure winds with. And what's the problem with that? We still have one working wind sensor, right? Well, the problem here is that when winds came from in front of the rover, sure, we could measure wind speeds and wind directions really well. But unfortunately, when the winds came from kind of behind the rover, the wind was messed up because it had to go around this very large rover mast on which the wind sensors are mounted. And up on the top right here is a computer simulation of what happens to flow as it moves around this mast. It gets really messed up. So basically the flow over here that this wind sensor is able to measure when the wind comes from this direction doesn't really bear much relation to the flow before it reaches that mast. So the best that we could really say was whether the wind was coming over the right shoulder of the rover or over the left shoulder. We couldn't really say anything about the wind speed, and we couldn't be accurate about the direction. Now, the solution to this is to point the rover in several different directions, and in each case for several sols, and that way you can measure the winds at all times of sol, because you'll have some measurements where the wind is coming in the right direction. to be measured by that front wind sensor. So this is how we did it. Just to show you, this is showing the end of drive location, and then the direction that this little line is pointing in shows where the rover was pointing, the rover heading. So basically, we started off by facing to the northwest, then we faced pretty much south, then we faced roughly to the east for a few sols, then we faced back to the south again for a single sol, and then we faced to the southeast for a sol. And finally, we faced to the south again for a few sols. So this let us build up a wind data set over several sols. And just to show the winds from the late morning through to the late at night, you can see here that the blue arrows, each line is a different sol going down the page, increasing. And the blue arrows are showing when the wind speed was good and the wind direction was also good. And then the red arrows are showing when we could only tell the wind direction to plus or minus 45 degrees, and we couldn't really say anything about the wind speed. And now what you can see is that as we changed the rover heading, we were able to fill in different times of sol as the wind rotated to be coming from the north and the northwest to coming from the east and the southeast later in the day. And so that really allowed us to get a much better picture of what the wind was doing over the full sol. And so this let us confirm theories about wind patterns inside Gale Crater as well, that basically during the daytime the wind is coming from sort of upslope, mostly from the northwest, and then at night the wind is coming from downslope, mostly from the southeast. Now, this is another great example of how we were able to try and deal with a problem. And I call this cleaning with dirt. Now, here we're back with the InSight lander in Elysium Planitia. And the thing is that unlike the Curiosity and Perseverance rovers, which use radioisotope thermoelectric generators, the InSight lander uses solar panels to generate its energy. And the problem was that these panels have been getting rather dusty. Now, on most Mars missions with solar panels, we've been lucky in that there have been regular cleaning events. And by that, I mean strong winds or dust devils have raised dust from the panels periodically and have been able to clean them off and leave them able to generate a lot of power. But unfortunately on InSight, the solar panels have just been getting dustier and dustier as dust falls out of the atmosphere onto them without really being cleaned off very much. And so on the right-hand side here, you can see on Sol 10 of the mission early on, the solar panel is looking pretty pristine, but on Sol 122, on the left here, the solar panel was getting extremely dusty already. And now we're really approaching 2 Mars years on the surface. So that's 2 times 669 sols. And really the solar panels are really very dust covered. Now, as a result of this, it means that the power available from the solar panels to do science or even just keep the lander alive during the cold night and during the coldest season, so winter, which happens to be when there's the most dust in the atmosphere as well that blocks out some of that sunlight, that power has been going down and down. And so it seems that the fine dust is very sticky, and the wind and the dust devils alone haven't been enough to clean the dust off those solar panels. So that's why the team came up with an interesting idea. What if we bounced particles of dirt off the solar panels? So this isn't as crazy as it might seem, because sandblasting, where sand particles actually help to kick dust particles up off the surface, is a very popular idea for how most dust might be lifted from the surface on Mars. And here's what happened when we tried it. Now you can see here the scoop that has a big scoop full of dirt or sand, sandy kind of mix of sand and dust in it, is dumped down onto the deck, and so you can see it landing on the lander deck here. And then you can also see off to the left where the solar panel is, this big darkening of that solar panel. So you might be thinking, as I did, I confess when I very first saw this, oh my goodness, it's just got a load of dirt on the solar panel, which you'd think would make it, even more covered up and even harder to get power from. But actually, what that darkening is, there might be a few bits of sand that are on there as well, but it's actually the sand having basically bounced across that solar panel and clean the dust off. And you can remember those pictures showing the pristine early solar panel. They were actually showing a much darker solar panel before the dust went on it and brightened it up. So basically what we're seeing here is a cleaning of dust off the solar panel by bouncing sand particles. And we also were able to confirm this from the fact that this one cleaning activity instantaneously recovered about 5% of the power that we had lost from the solar panel becoming dusty. So we could see that immediate increase in power and realize that that was due to the dump. Now, finally, we have a lesson from the Opportunity rover, and I think this is really impressive. So Opportunity got stuck in sand on Sol 446 of its mission, and you can see here a movie of many attempts to free its wheel from the sand. And you can tell there are many different attempts shown here, because basically every time you see that shadow move across, we're going to a different Sol. So that is actually the motion of the sun. So this is an incredibly speeded up bit of film here. And you can, if you count it, you can see there's 1, 2, 3, 4, 5, and 6. And then we actually start moving. So there are at least 6 attempts to free the wheel here before it finally gets going. And in actual fact, it took 38 sols, which works out to about 5 weeks on Earth, and over 20 attempts to get that wheel free. Now, the really significant thing here is that if the team had given up, the rover would never have moved beyond its location in April of 2005, which is shown by the pink star here. So that was less than 1 Mars year into its mission, and the rover would never then have done all the rest of this yellow traverse, and would never have got to the edge of this huge crater, and would never have been able to explore it. And so all of these images and these results and these amazing views and discoveries, none of them would have been possible because that rover would never have got there. So in conclusion, working on Mars is lots of fun, but you often have to persevere and get creative when the going gets rough. Thank you.